So hello everyone, and I'm Gilad from NVIDIA. And I have with me Professor DK Panda from Ohio State University. He has a plane to catch from San Francisco, so I'm going to start 1 minute earlier, and we'll finish hopefully 1 minute earlier. We wanted to present to you, to discuss with you cloud-native supercomputing, cloud-native supercomputing architecture, what it is, why is that important, what are the components, just be careful, and so forth. So first looking on supercomputing, maybe, or high-performance computing, looking on AI, deep learning. We are seeing that essentially deep learning or AI is going everywhere. Every company in the world will have AI. Every company in the world will have HPC infrastructure, high-performance computing infrastructure. Every company in the world will essentially have supercomputing. But supercomputing, or the supercomputing systems being used today, are not really set for multi-tenancy, not really set for serve, or to serve multiple users and to isolate between them. Supercomputing architectures which are being used for AI today are set for essentially a single user, focusing on getting the best available performance from the platform. That's what they are built for. So adding security and adding multi-tenancy and adding isolation is actually going to reduce from the performance you can get from a supercomputer. And that's why they don't really use those elements there, and they need actually to trust the users. On the other side, cloud infrastructures bring all the security and isolation, but they don't give you the bare metal performance. On every server you are losing around 25% of the compute capacity for the infrastructure workloads. So that's something that cannot actually be used to drive the complicated or complex workloads that we want to run. So essentially, we need to combine those together and to form something that we call cloud-native supercomputing. And cloud-native supercomputing is an architecture that brings bare metal performance on one side, actually accelerated bare metal performance on one side, with multi or secured multi-tenancy. And the element that enables to bring those two elements together, or to bring supercomputing to the cloud, is essentially the DPU. And the DPU was discussed in previous talk, the data processing unit. So before going into the data processing unit, I wanted to start talking a little bit about Infiniband as a network. And Infiniband is being used, is the most used networking technology for high-performance computing, most used technology for supercomputing, and it's getting more and more used for, or in AI infrastructures across the world, for high-performance computing clouds, like the clouds in Azure, and so forth. So why Infiniband becomes kind of a de facto also for AI? And the reason is because Infiniband gives you two kind of services. First, Infiniband is a network, so it gives you all the networking services. It's the only network that it's fully transport offload with RDMA. So moving data directly to the user space, if that's a CPU memory, or directly to the GPU memory, or directly from the storage to the GPU memory, and so forth. It's a network that leads with speeds and feeds. It's running 200 gigabit per second end-to-end for almost 3 years now, and yesterday, actually, NVIDIA announced the next generation of Infiniband, which is called Quantum 2, which is going to run 400 gigabit per second by the end of this year. So it's leading from the speeds, leading from a lowest latency perspective, brings adaptive routing, which is one of the advantages of Infiniband, to be able to spread the data as even as possible and get the highest utilization of the network, congestion control, quality of service, be able to build different kind of topologies, and so forth. It's a network that is very simple to manage. It's a pure software-defined network being designed like that before people actually knew what SDN is. Now, on the other side, Infiniband also brings in network computing. Computing engines that sits inside of the networking devices that enables to move algorithms or compute algorithms to the network. And computing algorithms are the ones that actually they're ideal place to be executed is on the network, not on the server. For example, data reductions. Data reductions are being heavily used in high-performance computing, meaning in scientific computing. It's being used for deep learning. And doing data reductions on the endpoint, it's pretty much the wrong place to do it. So moving the data reductions to the network, reduce latencies, provides flat latencies, reducing data motion, and a lot of other things. So Infiniband gives computing services as well as networking services, and that's what makes that the de facto connectivity for high-performance computing. Now, as we're looking on, or before going there, this is an example of the data reduction mechanism that exists on the network. Actually, those are a set of computing engines that sits on a data path on every switch. And that enables the switch fabric to build aggregation trees inside of the fabric, and on the application side to actually move the reduction operations to be done on the network themselves, on the network devices. So instead of sending data between the endpoints in order to do data reductions, you just send it to the switch network. The switch network does the data reduction and a broadcast of the result back, and does it much, much quicker with less data motion. But now as we're looking on cloud-native supercomputing and the need to combine bare metal performance and multi-tenancy, in order to do that, you need to actually migrate or move the infrastructure workload outside of the CPU. So if you move that outside of the CPU, you can keep or you can enable bare metal performance, and you can run more of cloud services on your system, on your supercomputer. Now the DPU, probably most of you know, it's a device that includes all of the NIC functionality, and it's marked here with ConnectX. So ConnectX is the NIC from NVIDIA. So all the NIC functionality is there. The DPU also includes multiple ARM cores, memory interface, so there is memory on the card, PCI Express switch, and other acceleration engines beyond of what I mentioned before for storage, for security, encryption, and so forth. So essentially the DPU, it's a full data center on a chip. And by placing that inside of the server, we're getting a new computer inside of the computer, a new Linux machine inside of the Linux machine. And that new Linux machine can actually run the infrastructure workload and do it much more effective than a host CPU. And the reason it's not because it's faster than the host CPU, and the reason is because it has dedicated hardware engines for the infrastructure workloads. So from a high-level architecture perspective, what we're doing here is that we're moving the infrastructure workload, the multi-tenancy, the isolations, the security, moving that out of the server and run that on the network, separating between the application domain and the infrastructure domain, which is actually a much better thing to do. Doing security on the application domain, it's probably the wrong place to do security on. Also moving the file system management, cluster file system, network file system, move that outside of the server and actually outside of the CPU, and running that on the DPU. So the full infrastructure management in that side. The other part, and this is going to be the majority part of the discussion here. So the DPU, we know it enables us to move the infrastructure workload. So moving that outside of the CPU and put it on the DPU. We separate between those two. And now we can bring the multi-tenancy and not losing any CPU performance. The other element is that the DPU gives us capabilities to actually do more than that. Actually, it gives us capability to start migrating the communication frameworks outside of the CPU, outside of the node, and put it on the network. For example, message passing interface for scientific applications. Shmem-Pigas, for example, for databases. Nickel, which is an NVIDIA library for AI, and so forth. It enables us to migrate those communication frameworks to the network, and that gives us the ability to actually achieve overlapping, which is a key thing for accelerating application performance. And by overlapping, I mean be able to progress the compute on the CPU while progressing the communication in parallel on the network, and achieving full overlapping between compute and communications. And that will be the majority of the part. So just before getting there, Obviously, on the security side of things, motivation is utilizing the DPU to move the infrastructure to become zero trust. Zero trust on the user, zero trust on everything else. You don't want to trust the user. You want to isolate the user inside of the server. The DPU connects to the BMC of the server, for example, and you do the full provisioning of the server and load operating system and cleans residual information between users and so forth. We also bring performance isolation. So not just tenant isolation, but also performance isolation. And this is something that we announced yesterday, and that's why it's not on the slides here, because those slides were done a few weeks ago. Performance isolation is an advanced capability that makes sure that one user job running on the network will not impact another user job running on the same network. And this is something that you don't see today on cloud infrastructures where one job can actually impact another job if they have the same quality of service attributes. So by doing performance isolation, you can overcome that problem. So moving to the acceleration part, so we have the infrastructure side running on a DPU, security isolation, performance isolation, and so forth. Now on the acceleration part of things, the way that we're using the DPU, it's actually by creating processes or DPU processes that runs on the DPU itself. Those processes can do data manipulations locally or data manipulations remotely, completely bypassing the CPU. Leveraging RDMA capabilities, leveraging the full transport offload, you can actually change or impact or do manipulations on the memory without involvement on the CPU. So that means that you can move non-blocking collective operations. You can use active messages. You can do progress threads done on the DPU. There is a lot of things that you can do on the DPU as part of accelerating application performance. So with that, I'm going to move this one to Professor DK Panda, which will discuss the work that he's been doing on the DPU for migrating MPI, or message passing interface, to run on the DPU.
Right, thank you. Thank you, Gilad. It's very nice meeting all of you and try to share some of the things what we have been doing with the DPUs. Just to give a quick background, I see a lot of familiar faces here. I mean, from my group, we have been working with high performance networking almost now for 30 years, starting from the very old days of Mirinet, Quadrix to Infiniband, Rocky, RDMA, and all those interconnects. So now since the DPU has come as a new kind of a technology, so we are here just to jumpstart and then see what can be done with it. That's what I'll be trying to say. So as Gilad indicated, one instances I'll try to show, this is the very first initial piece of work we have done, but there are a lot of opportunities here depending on the DPU, how much things can be offloaded. So here I'll be especially focusing on the MPI libraries. Those of you know, like MPI is very widely used, not only for scientific computing, but these days is very also widely used for all the AI, like you can do deep learning, machine learning, using MPI libraries and all. So if you want to get the best performance, of course, you want the low latency communication, high bandwidth communication, and especially minimum contention for host CPU resources to progress what is called these non-blocking collectives. Okay, so let me go into a little bit more details if you are not familiar. A lot of MPI jobs, let's say you want to exchange a lot of data. So MPI standard, it has collectives like AllToAll, AllReduce, Reduce, BCAS. So these are very widely again used for HPC and AI applications. Traditionally, in the many years back, it used to be only blocking collectives. So that means if I want to exchange a lot of, I do the computation, and then let's say I do AllToAll, it used to be a blocking call. So that means processors are not doing anything, but rather they are helping in depending on how that algorithm is implemented. Okay? But then what it shows that while the computation and communication are happening, there is no overlap. And that leads to scalability issues, performance issues. So this is why MPI 3.1 standard a couple of years back introduced something called non-blocking collectives. Okay? So the idea is that if I can rewrite my applications in a proper manner, I can do some computation and then initiate the communication. And while the communication is going on, I can also do computation. Okay? So it's just like a day-to-day job, means what many of us do. Like I just give this example to my students, like it was a Friday evening, you are waiting for your friend to come to go to a movie. You just don't sit idle there doing nothing. might be your friend takes 15-20 minutes to come to your house, you continue to do your work. So we are overlapping computation with communication. Okay, so that is the idea. Even though like MPI 3.1 standard introduced these, there was no really good solution. People have proposed like this CPU based non-blocking communication progress. So that means the CPU will go perform some computation, then try to help with the communication, but then you lose a lot of cycles. Okay, so you cannot do this efficiently. So this is where the DPU is now coming. So I call it like an executive secretary model. So think of like the host cores are now, the CPU cores are executives, and then the DPU, you have some ARM cores, they are secretaries. So just like in the day-to-day world, we offload a lot of things to the secretaries so that they can take care of some of the tasks, while the executives are free to do their own important decisions. And that's the model kind of things we want to bring here. So the challenge is, can we actually offload these MPI functions, and can we exploit these additional computing capabilities of the Bluefield DPU into existing MPI middleware? So that's what I'll present, but as Gilad indicated, I mean, there are a lot of opportunities. Any other middleware you can take, offload it, you will get the benefits, but we don't have those solutions yet. So especially here, I'll try to show for dense non-blocking collective communication. So this is like a typical DPU architecture, which was introduced earlier. This is the Mellanox NVIDIA thing. So you can see this is the ConnectX 6 architecture here. This is the 200 gigabits per second. We have, these are the host cores, and these are the programmable ARM cores. And it is a full-fledged system. So you can actually do based on, like, you can log on to this node, and you can actually run application there in the DPUs. So now the question is, how do we make, these are the executives and these are the secretaries, and how we can make them work together to get the best performance. So in this context, let me introduce the MAPIS to MPI library. Some of you might be familiar. If not, we introduced this project almost 2000 when Infiniband was the day one. Prior to that, we were working on Myrinet, Quadrix. So when Infiniband came, we were the very first ones from my group to jump into designing a high performance API with RDMA. And for 20 years, we have been continuously working on this project. So it has a lot of features, like we take care of all the different networks, as you can see here, Infiniband, IOR, Procky, Omnipath, even the Elastic Fabric adapter from AWS. And then now, especially here, we are trying to explore these Bluefield DPUs. Okay. So then what we did is we tried to bring a framework, just like executives and secretaries talk to each other. So we need to have some kind of a communication framework. Of course, this is currently being done for Mellanox / NVIDIA DPUs, but it can be customized. It can be modified for any other kind of a DPU architecture. So what we introduced, something called a worker process. So just like I said, secretaries, so think of them as worker processes for the DPU. And the Bluefield is set to a separated host mode. So that means we can move data between the host memory and the DPU memory. So these worker processes are spawned to the ARM cores of the Bluefield. And once the application calls a collective, host process prepare a set of metadata and provide it to the worker process. So just like the executive, let's say, wants to decide, saying, okay, we want to have 5 video conference calls with these people. Okay, so the executive gives that task to the secretaries. So like this, we create some metadata and then some kind of a data exchange. And then once the worker process get that, they are totally independent. They can continue. So in that case, we don't need any involvement from the CPU process. And then once the message exchanges are completed, worker process notify the host process that it has been done. So it's just like the secretaries. They set up the conference call, everything, then send the Zoom link to the executive saying, yeah, these are set, this is on the calendar, so you go ahead. So that is the kind of the broad framework what we are trying to bring. So now let's go into a little bit details, how actually we implement this. So this is an example of AllToAll, okay, non-blocking AllToAll. So here if you see, so we are combining this RDMA. So let's say this is the host memory, this is the ARM core. So instead of the regular host-to-host exchange, you can actually send a data. Either you do a RDMA write, or you send a message, and this node does a RDMA read. Okay. But now what we can do is, instead of that process, host-to-host communicating, we go through this 3-step approach, or a 2-step rather. So here we can do an RDMA read. So that means once those tasks are given to the worker process, an ARM core can actually go do an RDMA read, and then actually it can do an RDMA write directly to the host memory. not to the other ARM core. Okay? So, it is just 2 step. You can do a 3 step, but that may not be good. You can always do an RDMA read, RDMA write, and then this one does RDMA write. But since these are operating on individual host modes, this ARM core can actually write to this host memory. It has the RDMA capability to there. And then that is the basic step. So, now you can take it into the actual algorithm. Okay? So, let us say AllToAll is a very dense communication. That means I need to send data, like if there are n processes, I need to send individual messages to everybody else. Okay? There are different algorithms, but simple algorithm is like this. So, here what we do is we try to orchestrate. So, in this case there is an example of scatter destination algorithm. So, as you can see, like the first is a step 1, we are trying to do like these are like P0 to P3, these are the host cores, these are the worker process, they are doing individual things. So, then in the step 2 they are doing 1 step apart, step 3 they are doing 2 steps apart, 3 steps apart, like in this n-1 steps you can actually finish. Okay? So, basically these ARM cores are reading, writing, and this can happen in a pipeline manner so as to overlap the computation and then try to reduce the things. So, let me show you some numbers. So, we have actually this algorithm is already published, we have actually a version ready. I'll show that number. So, we carried out this in the HPCAC cluster. So, these are some of the specifications. So, we have a enhanced version of library called MHAPIS2 DPU. Okay, I'll go into that. That is already publicly available from a commercial spin-off called XScale Solutions. I'll introduce that. So, if anybody has a cluster to try it out, we can actually share that with. So, here I'll try to show some numbers, and here we are using the standard OSU micro benchmarks, which comes with the MHAPIS library and it is very widely used in the HPC field. So, we are just using the standardized benchmark. So, it is an AllToAll benchmark, that is a non-blocking AllToAll. So, there are some parameters here like pure communication latency. That means, if I offload things to the ARM, what is the time it is taking for pure communication? But that is not important. The important is how much overlap can I get, and then the total execution time when I do communication plus computation, because that is the objective. So, might be the pure communication latency we are getting a little bit slowed down because the ARM cores are not that fast, it may take a little bit more work, but the question is if I put overlap of, if I do a computation and communication, do I benefit or not? So, now you can see this is the first set of numbers. So, this is a 32 nodes running OSU AllToAll. So, this is a 32 node 32 ppn like a 1000 process, and here it is a 512 process. So, those of you are familiar with MPI libraries, there are broadly 2 protocols. One is eager protocol for short messages and rendezvous protocol for large messages. So, if you see the basic MHAPIS2, which is a host driven thing, to implement this OSU AllToAll, see this red bar, very tiny. So, there is no overlap because the CPU is itself involved in trying to take care of that communication. But now, if I offload, just like that executive secretary model, see the overlap suddenly jumps up like a 98%, 100%. We can get the overlap between computation and communication. So, here we took actually this is the both computation and communication being put together. So, the same set like a 512 process, this is 1000 process, and these are the message size increases. Now, see the basic MHAPIS2 where computation and communication cannot be overlapped, it takes more time, but now with this overlap with the MHAPIS2 DPU library, we can reduce the execution time by 22%, 18% depending on the different message sizes and all. And this is a very first cut design, we are several enhanced designs are in the pipeline and they will be pushed very soon. So, that is just at a micro benchmark level just for AllToAll. So, now then what happens is we went to the application. So, one such application we are using here is the P3DFFT. This has been designed for San Diego Supercomputing Center. So, here one key thing is that just like the example if you remember I gave saying your friend is trying to go to a movie and you are coordinating. So, that means the application needs to be redesigned a little bit. The traditional application if you just have a blocking AllToAll and now I just changed to non-blocking AllToAll, you should not see any benefit. Okay. So, you need to restructure the application and that is what we did. The developer of this P3DFFT, Dimitri from SDSC, we worked with them. So, he totally reorganized that P3DFFT code, so that you can actually do some part of compute, then do a non-blocking AllToAll, but while the non-blocking AllToAll is taking place, I can also do some more computation. Okay. So, now that actually matches with this new DPU framework. Okay. And now, if I put all these things together, the hardware and the software, now you see in the P3DFFT, this is 16 nodes, So 512 process runs, 256 process run, the overall application execution time. In this case, we are getting like 18%, 20% benefits. Okay, so it's the same hardware. If you can enhance with the DPU, additional ARM cores, and the software, you get this kind of benefits. So similar kind of things. Now you can think of all other collectives. So there is an AllToAll gather. That is also another primitives there. So now we see big benefits. In fact, 41%, 48% kind of things. Broadcast, that is again a very commonly used collective. So now we get almost 60% benefits. So these are some of the initial numbers, and we have actually this MRPs to DPU, which is already available, and you can actually go and then contact us. So this is being done with a commercial spin-off called Xscale Solutions, and you should be able to actually try it out for your applications, and we'll be very happy to also to get engaged with you if you have any of these applications to really demonstrate the benefits of the DPU technology. So might be now I'll hand it over to Gilad, and then he can continue.
Yeah, thank you for that. And the combination of the in-network computing capabilities of Infiniband with the DPU, it's a great combination. For example, data reduction operations are not going to be run on the DPU themselves because data reductions are actually running on the silicon of the network. And it get you flat latencies in a single digit. So the overlapping is fully there. Now, the rest of the elements that are not part of hardware engines, those parts are being migrated into the DPU, and you can see the benefits of that. So the combination is great. We are also, from the NVIDIA side, build a software development kit and runtime called Doka. Doka to the DPUs is similar as CUDA for the GPUs in that sense. Doka expose all the services of the DPU to the applications running on top of that, and ensure that everything that was written on one generation of the DPUs will carry to the second generation and third generation and so forth. So with that, the slides I assume will be posted. So there is more links here to learn more about cloud-native supercomputing and open source development around APIs to access the computing on the network, such as Open Smart Network API that is being done as part of the UCF consortium. Link to the Mvapich 2 DPU library is here too, if people want to get access and start using that, as well as some recent news about it. And with that, we'll want to thank you very much for listening.
Are there any quick questions anybody has? Yes.
So is this strictly limited to Infiniband implementations, or that work over Rocky?
No, you can use the DPU is a device that can run Rocky as well,
yeah,
or Ethernet or Infiniband, and you can use that part as well on the Rocky side of things. The advantages of the Infiniband part are mainly first latencies and speeds, feed and speeds. The ability to actually Infiniband is a full transport offload, so the rest of the there is no transport that's being done on the CPU, so that's actually moved more things to the network. Another part is that it has several elements already in hardware. For example, the reduction operations, barrier, AllToAll operations is now coming in hardware, tag matching, and so forth. But if you want to use it on a Rocky infrastructure, anything that was done on the DPU can also work on Ethernet infrastructure as well.
Yeah, and MFH 2 supports Rocky. It has been supporting Rocky V1, V2. But what I showed the result, they have been just evaluated on Infiniband. But we can make it work also on the Rocky environment.
Sure.
Okay.
Thank you very much again.
Thanks a lot. Yeah.